Welcome, everyone. Good afternoon. Let me see some more students. Admit all. How are you guys doing? Okay. Let me just look at the chat. Good. That's good. I'm doing great. I'll just wait another minute for students to join. Were there any questions? How did you guys do? Sorry, I posted the answer key a little bit later, but did you guys get a chance to review it? And how did you do? And were there any questions from that that you wanted to discuss? 1A, 5, and 6. Okay, very good. And it's very possible. I kind of was in a rush when I wrote those up. So it's if your answers don't match with mine, it's possible. Let's see here. Admit all. What's going on with my? Oh. All right, let's go over those. So. And then we'll try to get through some of the material for the lesson. I also posted a homework that will be due next week. So you guys can take a look at that over the weekend. All right, 1A. So for number 1, in general, this is a really good problem to know how to set up. I recommend drawing a table because it's really hard to just do this just by reading it. So you have students who major in comedy and drama, and you have male and female students. So you get something called a contingency table. Just kind of breaks up things into different categories. And I'm just going to fill out this table really quickly. 19 of the female students study comedy, and 27 do drama. And then 14 of the male students do comedy, and 38 male students do drama. And the question was, what is the probability of drama or female? Okay. So to find drama or female, we're interested in the probability of picking somebody from this region, this orange region that I'm highlighting. That's how I would think about it. Or, oh, I see. Angel wrote that's a good comment there. Be careful. I think it was 38. Yeah, be careful here. I actually believe I say the thing about what I give in this table is the actual like people in each category. So this is not one where, for example, the probability of female is going to be 19 plus 27 all over. Let's just do it really quickly. This is 52 total here, and then 30, 46 here. So I believe the total is 98 overall. So probably a female is 19 plus 27 all over 98. So you could do it using that formula. But I find the easiest thing to do is just to add up the orange squares. So in this case, it would be 19 plus 27 plus 38 all over 98. But if you see another way you can get that answer using the formula that we learned is probability of drama is 27 plus 38 all over 98. And probability of female and drama is that overlap region. It's this one, this red one, equals 27 over 98. So hopefully you see, if we do the formula, and I wouldn't recommend doing this way. I'm just showing you, so just to show that the formula works. But I would just recommend looking at the picture and saying, okay, female or drama, that's going to be this shape right here. That's all. So you don't need to do much here. But just to show you that the formula works, just and to remind you what the formula is, you can say that the probability of a union is equal to the probability of each one of them. You see, if we add these guys together, this one plus this one, the 27 over 98 gets counted 2 times. So then we subtract it off 1 time, so that we end up with exactly the formula that we wrote earlier. So that's how you could apply that formula. All right. Any questions on 1A? Any other questions? Does everyone feel, or anyone have, just a show of hands, do you feel like you could, if you saw this question on the test, you would, no problem, ace it, basically, if as long as you read it carefully? And and know if you feel like you maybe feel a little bit shaky on it. Especially part B and C. So any kind of what could I explain, or what this whole thing, I didn't mean to kind of make it more complicated than it is. Is there anything I can kind of highlight in this problem that would clear something up for number 1? And by the way, please have your exam, the practice exam, if you can, just up on a separate page so you can ask about it. All right. And then number 5, and feel free to ask about, those of you who just joined, you can ask about any question that you guys want. So number 5 would be, so this one again is, yeah. So should I re-explain part 1, 1A? So we just did 1A. 1A was drama. The question, what's the probability of finding a student who does drama or is female? So that corresponds to first we created a table, and with the information we're given, kind of breaks up the population of students into disjoint categories. So none of these overlap. You can't be doing a double major in both in both comedy and drama. You're either doing one or the other. But what about the chance that you're either studying drama or you're female? Well, if we pick a student random, doing that, you look at the total population of students, there's 98, and the ones that match this category are just this region. So you take all the drama students, but you also have to include the possibility that in addition to studying drama, maybe they're just, maybe you include the students who are also female but studying comedy. So you add these 3 numbers. That's it. And then for part B and C, it's like a conditional probability, where what's part B say? If we know that the student is male, what is the conditional probability of the student study drama given that he is male? So that would be focused on, given that the student is male, what is the probability that student studies drama? So out of this universe, what's the probability that they are studying drama? That's 38 out of 52. Did that help clear it up? Okay, I'm gonna go to, awesome. I'm gonna go to number 5. So this is again going to be a Bayes question, which you guys will expect to see. We have a computer virus spreading across Facebook. So right away think, okay, we've seen a bunch of these types of questions. Kind of a famous thing that Bayes' theorem is for, is figuring out if something is actually infected with a virus or not. And then Facebook has some sort of software test to identify if an account has the virus. And maybe the test that it has is like, maybe you're posting a lot of memes unusually, right? And obviously maybe you're just doing that by your own choice, or maybe it's the virus. So it could be either way. That's kind of like an example. So it makes the test, and the test has a 90% accuracy if the account is affected or has been infected with the virus. So the hidden state here is whether or not the account has been infected with the virus. So this is virus. This is no virus. And so far, 4% of users. So that only 4% of users have been affected, and 96% of users are not affected. And then we have a positive and negative test to decide if it's been affected or not. So we write positive, negative, and we'll test positive, which means the test identifies that there's a virus. This is correct 90% of the time for somebody that has the virus, for some account that has the virus, and it's incorrect, therefore, for 10% of the time. And this is the tricky thing. This number is not given to you, but you just have to figure it out that, okay, if 90% of the time it'll test positive, that means that the other time it'll test negative. Does anyone know what this branch is called? What type of mistake this is? It is an intersection of two things, but in this sort of testing, exactly. Angel, you want to share what you said?
False negative.
It's a false negative. So it's like you got a negative test saying, oh, you don't have the virus, but but in reality you do. Okay, so very good. And also, it is an intersection of two events as well. Okay, then no virus. And no virus, you know what? We don't get a positive test. It's not very likely to get a positive test if the account doesn't have a virus. Only 2% chance of a false positive. So that goes over here. And that makes sense. Like, you know, they wouldn't design a test that would, they should try to keep the chance of that happening to be pretty low. And then therefore, if the account doesn't have the virus, then there's a really good chance that it's going to test negative. All right. So I really would hope to see this type of tree when you guys solve this problem. And for me personally, it's very hard to solve this problem without drawing this type of tree. There are ways as well to do it with charts, but I personally like this one. And then they're asking us, what is the probability that it has the virus given that the test was positive? Well, I just have to look at all my positive branches. So I'm going to highlight them in purple. So those are my possibilities. That's the part of my population or that would get test positive. So it's going to be the top branch 0.04 times 0.9 plus 0.96 times 0.02. And the idea is because this is really small, this percent is really small, this number is close to 1, so this will be 0.036. So this will be pretty close to 0.04. But the interesting thing is that this number is actually also, even though the percent here is really low, only 2% chance of getting a false positive, because it's the prior here, that the number of people that don't have the number of accounts that don't have the virus is really high. Even this small percentage of getting a wrong result will mess up your will throw off your what you expect to see. So this will actually make this number comparably large to this one. And the numerator is going to be those positive tests that actually have the virus. So let's do it in color here. This is that. Okay, the one is the bottom one, and then the red one will be on top. Yeah, it will be 24. And I forgot what the answer was here. Let's see. 65%. So again, the important interpretation here is that because it's a fairly rare virus that's spreading across these accounts, just because even if the test is really good, just because it got a positive result, doesn't necessarily mean that the account has been infected. All right, and then number 6. Oh, did you mean the one the extra question with Shaq? So the question with Shaq was about binomial probability. And you can practice some of these. I think there's a section on Khan Academy as well. But it's related to the binomial theorem. So Shaq has a 30% chance of making the shot. And each shot is independent of the last, which obviously that is a kind of a big assumption. And then let's say he takes well, that is number 6. Okay. Wait, did you guys want to go over that one or the actual? The thing is, I don't think I'm going to ask about 6 and 7. I can go over those. That is one of the things. Yeah. This question, I wrote it in the comment. It wasn't in the actual practice, but I'm going to replace this question with. I'm going to replace 6, 7, 8 with this question. Because 6, 7, 8 we did previously. So I'll just kind of go over this one. So just take a note. And we went over it in class too. I go over it in more detail, I believe, in one of the lectures. But Shaq has a 30% chance of making a shot, and each shot is independent of the last one. And he takes 6 total shots. what is the probability that he makes exactly 4? Well, we can think of this as probability of that yes, he makes it is 0.3. The probability that no, he doesn't make it is 0.7. And because it's independent, because each chart is independent of the last, what will be the probability, for example, of yes, yes, making the first two, then missing one, then making the next two, and then missing the last one? What do you guys think? What would be a good expression for this specific sequence of events? He makes the first two, misses one, and then makes the next two, and then misses the last one. And they're all independent. It would be a really simple expression. And you guys can chat it to me also for this event. Any volunteers? What's the chance that he makes a shot and then makes another shot right after? Be careful, not plus, but times, right? Because it's kind of like a tree diagram. And so this is all about the multiplication rule. The chance of first you have the probability of if they're all independent, then the probability of a sequence of events should be just the product of each independent of each event. Exactly. Nice. Fiona, do you want to share what you wrote? I really like that.
Basically, I just we know that there's a 30% chance of him making it, so that's why. So then you do 0.3 times 0.3, and then there's a 70% chance of him not making it. So then you do times 0.7, and then again times 0.3 times 0.3, just following that pattern, and then again times 0.7.
Awesome. So I'm just going to write it like this here, like this. And just kind of I really like the way you wrote it out, because it shows what's really happening, right? That first shot, you can think of like the multiverse, if you've been watching Marvel or stuff. If there's 100 different universes, in 30 of them, Shaq will make that first shot. And then in 70 of the other ones, he'll miss that first shot. But then out of those 30 universes where he made the first shot, then he's going to make in 30% of those 30 universes, he's going to make the second shot. And so you can kind of keep digging in deeper through all the possibilities. And Lily, what did you write? That's a great way to summarize, because it's multiplication. What notation can we take advantage
of? So I did 0.3 to the fourth power times 0.7 to the second power, just because you're combining all of them.
Exactly. Awesome. So this is the key idea, that this specific event of making the first two, missing the third, making the other two, and missing the last one, it has this probability. Now the cool thing is that we're saying makes exactly 4 shots. So this is not the only possibility to make 4 shots. How many other ways are there for Shaq to make 4 shots out of 6? What tool do we have to count them? Nice. And Angel, which combination would be helpful here? Combination is a very good idea here.
6 choose 4 for the ones he makes, and 6 choose 2 for those that he doesn't make. But
Exactly,
Okay.
and those would be the same, right? Because you can either think of it as I want to pick the 4 shots that where I place the yeses, or alternatively pick the 2 shots where he makes them. Very good. So this is just the probability of making exactly 4 shots, exactly 4 out of 6, is really just 6 choose 4 times 0.3, or just to kind of keep it consistent with something we learned earlier with the binomial theorem, we can focus instead on the shots that we want to label as misses. So it's like picking 2 friends to not invite to the movie with you. It's 0.3 to the 4th power times 0.7, please. And if you look at these terms, this is the, we might have talked about this a little bit before, but just to mention it again, this should remind you a lot of binomial theorem. Now look at this. What do you guys think would happen if I added up all these numbers? What is probability of making exactly 0 out of 6 plus probability of exactly 1 out of 6, probability of exactly 2 out of 6, all the way to probability of exactly 6 out of 6. If I add up all these possibilities, what should it be, obviously? So Shaq goes and he takes 6 shots, and I say, what's the chance that he makes either 0, 1, 2, 3, or 5, or 6? What should all those probabilities add up to? Nice. Yeah, very good. So, Angel, do you want to share what you said?
The result of all probabilities adding up should be 1.
Nice, right? Because it's all possible events. When Shaq takes 6 shots, either he makes none, he has to make some number, either none or all 6, or somewhere in between. So this has to be equal to 1. But on the other hand, if you look at this formula, where it comes from, how it looks like, this is really just equal to, it comes from considering this, 0.3 plus 0.7 raised to the 6th power. Nice little, very good. And do you guys see that 0.3 plus 0.7 is just 1? So if you raise it to the 6th power, it's just obviously going to be 1. But the interesting thing that happens is when you expand this, with the terms, the individual terms that you get with the coefficients, they correspond exactly to these individual probabilities. Okay, any questions on that concept? How many of you feel like you see the connection between this question about like there's some success and chance of a success and a chance of a failure, and you repeat that event, you repeat that over and over. But where's the and seeing the connection between that and the binomial theorem? Do you guys? And look, the final answer actually simplifies to the final answer. I believe I put it in the calculator. Was just pretty low. It was about 5%. Okay. Any other questions from the review? How do you guys feel? Do you feel like you do well on this test, or need some more studying? You can message me. Is there any concept that's on this test that you nice, very good. I'm happy to hear that. If review a little bit 2A. Oh yeah. Yes, I'll post this. What to use? What do you mean by which one to use? Oh, which one? Okay, yes, yes. Adam, correct. Yes, 6, 7, 8 will just be replaced with a binomial probability question. Possibly, yeah. Email me if you want to do some office hours. Maybe the Sunday might be better, actually. Yes, send me an email if that's something you'd be interested in. Brendan, for the one with this one, I just plugged it into the calculator. This came out to be 0.036, and this was like I don't know exactly. I think it was like 0.56, something like that. So I just plugged. I calculated the numerator and I calculated the denominator separately, and then I divided. And then one's going to ask about 2a. For number 2, 2a. Again, number 2a is an interesting one where I'm just kind of really testing to make sure you see that we can talk about independence in a very abstract way. So 2a, first saying, what's the probability of A intersect B? Well, we know that based on what we're given, the only way to find that is probability of A plus probability of B minus the union. Probability of A union B. This is if you take the two pancakes and you want to find the overlap, you can just take each one separately and add them together, but then subtract out the union, and that would give you the middle part. So using that information, we get 0.7 plus 0.4 minus 0.82, which comes out to be 0.22. All right, let's go through, and I want you guys definitely review some of the tests and ask me if you have any questions on these concepts. But let's start the next section so that you have time to go through some of the homework. Okay, so today we're going to discuss probability distributions and random variables. So I'll kind of mention this here. So probability distribution is similar to something we call a frequency plot. So a frequency plot is you collect some data, and we'll talk about the type of data in a second, and you plot your outcomes, the possible outcomes on the x-axis, and then over here on the y-axis, we'll plot the percent frequency, how often those outcomes happen. So just to introduce, there's three types of data that might encounter. So there's something called quantitative data. And this is data that you can actually measure. So anyone having this is a really wide open question. Any example of a data set that you can go and collect that would be an example of some quantitative data? This is data that you can measure, and you can actually comes from some sort of scale, and not just a scale, but some sort of continuum. Yeah, store profit is a good one. So something like about maybe how much money the amount of profit a store makes. You go to different stores and you can see how much money they make. You can also do like height. People's height is a good example. Yeah, so there's lots of time. You can measure like if you're working at the Tesla factory and you're testing the batteries, you could say, oh, how long before each battery goes to 0%? How long does it take the battery to discharge? You want to do quality control, so you can do also time. There's lots of examples of quantitative data. So this is the most, this course will be focused on talking about quantitative data mostly. The other types of data are also interesting, and it's important to be aware of them. Have any of you ever heard of ordinal data? And you've all actually seen this for sure. Anyone guess what ordinal data is? Does anyone know what that is? How many of you have ever taken like after like you call customer service or you go to like an amusement park or some like restaurant or something? How many of you have ever taken a survey asking about your experience? What kind of questions do they usually ask you? And how do they want you to describe it? Like,
were you satisfied? Describe it on a scale of 1 to 10.
Exactly. So if somebody says, "Oh, I'm like 8," like my scale of being satisfied is number 8, that's not really something. They do ask, "What could you do better?" Also, they ask this a lot for recommendations as well. Like, how would you describe the student's aptitude? Is it low, medium, or like high or exceptional or something like that? So ordinal data is where each data point kind of comes from some sort of scale, but you can't compare different people's responses with it, right? Like maybe one customer's like 8 level of satisfaction. We provided the same service, but maybe one customer gives an 8 and the other customer gives a 6. So ordinal data is a data that seems to have numbers because you can. It's based on a scale. But the measurement can be subjective. And so just be aware, like a lot of times people try to do statistical analysis on ordinal data, and it's a little bit tricky to do that. So if you ever and this is what business people love to do, because they love to give out these surveys to see what they can improve. And so the theories that we're talking about, going to talk about in this class, they apply to like very concrete things, like counting the number of people that say yes. That is a quantitative thing, like counting the number of people, or looking at average height, something like that. But looking at like average satisfaction score, and then if you like change the product a little bit, does the satisfaction score increase? There's some arguments about whether what theories we can apply, but just something to be aware of in general. And the last one is qualitative data. Does anyone know what qualitative data is? Any ideas how, have any of you heard of that term, qualitative data?
Qualitative is something that can't be like quantified.
Yeah, it's basically like when you're measuring you could be measuring like it's something that can't be quantified. Maybe like the color of people's shirt, like what shirt, what is the distribution of colors for the clothing that the store sells. So this could be data, this could be something that can't be put on a scale. So not compared. Like you can't say that a red shirt is higher level than a blue shirt or something like that. So not comparable to each other. And this could be represented maybe with a pie chart or something like that. Yeah, so when the census is a good example. When the census goes and like tracks ethnic backgrounds of people, and they get percentages of where people are from, that would be an example of some qualitative data. And it's data that you would represent, or maybe like if you look at a college and you say, okay, how many math majors are there? How many English majors are there? How many drama majors are there? That would be the rather not asking that question, but saying keeping track of is each student like what's their major? Recording their major is a qualitative data point. The number of math majors, that could be considered as a quantitative data point. You're calculating the number. So in general, if we're looking at the number of quantitative data, we can, and these other types of data, we can't really do this because we don't have an x-axis that visually represents the different outcomes, right? Because it's not fair to put like, it's not fair for ordinal data to put like, make a chart, a graph of like satisfaction score of 1 to satisfaction score of 10, because even though you're sort of implicitly saying they should, the intervals kind of are equally spaced, who knows how, maybe 9 and 10 are really close for people, but like 3 and 4 are far apart. Who knows how people think about that? So it's not a really consistent way of doing it. But for quantitative data, everyone can agree that if the store makes 10,000 versus 5,000, everyone knows how far apart that is. So there's a consistent a way of measuring the data. So you can plot, you know, I'm going to put over here like outcomes, and you can make this what we call a frequency plot. So let's say there's stores that make 0 to 1,000, 0 to 2,000, 1,000, 2,000, and 3,000, and $4,000. This is the outcome. This is going to be profit. And then you can say, okay, maybe a very small percentage of stores make a little bit of money. Then most stores make $1,000 to $2,000, and then some percentage of stores make 2,000 to 3,000, and maybe there's a very like high-end store, like an Apple store or something, that makes like a lot of profit, something like that. So this would be an example of a frequency plot. Also similar to we call it a histogram. Now, this is kind of how we could represent data if that were collected. There's also a way to represent something that we're describing abstractly if we know its probability distribution. And so let me show you a really simple example of what I'm talking about. So if you roll a die, one way to describe what could happen is by using something we call a random variable. And I think I'm sure everyone understands kind of the probability, if you just have a fair die, what's the probability of getting any outcome? So what a random variable is, and it took me a while when I first learned, first was taking statistics to kind of accept or understand what people are talking about when they say random variable. So a random variable represents two things, and one thing you can always have in the back of your mind is it can be represented as a chart. So the chart consists of two things. So the x is some unknown number that might pop out. And so here, we call the overall random variable capital, like script x. And capital script x represents the whole table. And we have a lowercase x, and it's a little bit different than like a lowercase x in algebra. It's similar, it has some similarities. The difference is that the lowercase x can't just be any number, but or I guess if you could think of it being any number, but the idea is that it could be any given possibility that it might be has an associated probability. So just to show you this table. So if you're rolling a die, what are the possibilities? Well, you can get x could be either 1, 2, 3, 4, 5, or 6. And the probability of getting a 1 will be in the P of x column. This would be 1 out of 6, 1 out of 6, because every roll is the same. Number 4 is also 1 out of 6. And number 5, getting a 5 is going to be 1/6. And getting a 6 is also 1/6. And that should be me. So the random variable that represents rolling a die is this entire table. Now, this table, I didn't write the number 7, but I could. What is P of 7? if my random variable x represents rolling a die? What would p of 7 be? What's the probability of getting a 7? It would just be 0. Exactly. What about p of if x is equal to negative 0.3? What's the chance of the die rolling and giving me negative 0.3? It's also 0. So this is kind of an idea of why we call it like an x. It could represent any number. Oh, the probability, so hang on. So this is the thing about random variable. Random variable is the entire chart. So the little x is a set of random values that you might observe. And the second column is the chance of observing those. So you're totally right. One student said a probability cannot be negative. Any number in this column can never be negative. However, in this column, you could actually technically write any number that you want. And maybe it happens, maybe it doesn't. Like, for example, imagine you had a dice, a different dice, not a dice that says 1, 2, 3, 4, 5, 6, but a dice that says -1, -2, -3, -4, -5, -6. So that would represent another random variable. And there's a nice way to visualize this situation is we can draw a frequency plot, and we call that a probability distribution. And I'm going to draw it as a bar graph, essentially, as a histogram. So what we draw is like this. So we have our outcomes here, 1, 2, 3, 4, 5, 6. And we keep in mind we only have discrete outcomes, so we can actually do this as a bar graph. And then, because every outcome is identical, has identical probability, I just have a set of like little bars that are all the same height. And then in particular, I know that the chance of getting a 7 is actually 0, but I don't even need to draw it. So this would be the a probability distribution. This graph is like, if you graph this like the x-axis, and this is like p of x, we say that p of x is the distribution. And yeah. Now, what if so what if I transform my random variable? So rather than labeling my dice as 1, 2, 3, 4, 5, 6, what would happen if I did a random variable? If I took my dice and I multiplied everything times 2, what would that look like? Well, I just have to draw the chart. And if you always think about the chart, or sometimes the graph, it really makes things a lot clearer. So in this case, let's consider 2x. So now, my outcomes, let's say I'm going to write it, use a different letter here. I'm going to use little y and p of y. Then I'm going to say let script y, capital Y, be 2x. Well, what are my possible outcomes? If my original outcomes were 1 through 6, but now every number I get, I double. What are the possible numbers that I can get as an outcome?
Would that affect, so like, for example, if x equals 3, would that just mean instead of 3, it would be 6?
That's it.
Okay,
Yeah.
so that would just be, it would be 1, 6, 1, 6, 1, 6, zeros all the way down.
Yes. So the first is what are the actual things that you can observe? So the first column is like what are your observations if you roll a dice that came from doubling the regular dice? Well, you can get 2, 4, 6, 8, 10, 12. The second column is the chance of observing something like the variable taking on that value. So the chance of observing the 2 is 1/6, 1/6, 1/6, 1/6. So it's basically just the same as a single die, but all the numbers on it have been doubled. That's it. Any questions so far? And this is where it's going to get a little bit interesting, where it's kind of we have to be careful. So another way we could have thought about this is if we have a die, rather than kind of doubling all the numbers on it, if we have a die that's like an identical position, like an exact copy, and it moves like exactly the same way, it's like a pure clone of the other die, and they always roll together, and then you're adding the two identical dies together. But what if we instead create a random variable that's a little bit different than that? What if the random variable is, so let's say let x1 be a die, represent a die, and x2 is another die. What does y equal to x1 plus x2 look like? What is the table going to look like? And what does it represent? What do you guys think? We had actually studied this before. What are the set of outcomes if you let x1 be a die and let x2 be a die, and then you add them together? What are the things that you can possibly get for y? Does anyone know what the range of outcomes will be? Well, this is related to the problem that we first studied when we talked about probability and sample space. If x1 is a die and x2 is another die, what is the lowest possibility that y could ever be? What's the lowest thing you can get if you add two die?
2.
2. What's the biggest number you can ever get if you add two die?
12.
12. So it looks like it's setting up to be similar to this, right? Because this was the lowest was 2, the highest was 12. But you'll see something different. What are other possibilities that can happen if you have one die and then you roll another die? But they're not the same.
You can have multiple ways to get the same outcome, thus making it a higher probability you'd roll one number over another.
Yes. And in particular, you can actually get any number in between 2 and 12, right? What's the probability of getting a 2?
12th.
So what's the only way that we can get a 2? This is little y. Nice. Keenan, what did you suggest?
You can only get it if you get a 1 and a 1.
Nice. And what's the chance of rolling a 1 and then another 1?
1 in 6 and 1 in 6.
Yeah, so, and since they're independent dice, the chance of getting a 1 and then another 1, we can use the multiplication rule. If you remember that table that we did, the grid, where we said, the first roll and the second roll, and we looked at all the possibilities. There are 36 different outcomes, and only one case of them gave us a 2. So the chance of this one being the 2 dice adding up to 1 is 1 out of 36. Now, this is possible because you're rolling x1 and x2. You have to roll the first one twice to get it up. Oh no, x1, so the way to think about x1 is a dice and x2 is another dice. There's nothing that says they can't be one at the same time.
Oh, okay, sorry. I was thinking of the 2x, I guess.
That's right. 2x is different. Exactly. 2x is x plus x. So it's like what you're doing there is if you're like, one way to think about all these things with random variables is like you're a scientist who's recording some sort of random experiment. So in x plus x, the scientist looks at the dice that was rolled and writes that number down, and then without touching it, writes that number down again. That's why it's x plus x. This is going to be always the same number plus itself. But in x1 plus x2, they roll 1 die, they get a number. Then they roll another die, and they get a number. So it could be 2 different numbers, for sure. Or it could also happen as the same number. But anyhow, the point is that this is related to what we saw earlier. This is the different ways you can, the probability distribution of when you roll 2 dice and you add them together, what's the probability of getting that sum? So we saw the number of ways to get the 3 is 1 plus 2 or 2 plus 1. So it's 2 out of 36. This would be 3 out of 36, because you can do 1 plus 3, 2 plus 2, or 3 plus 1. 4 out of 36, 5 out of 36, and then this was going to be 6 out of 36. And you can keep going down. This now, the number of ways to get an 8 is actually less, and it keeps dropping down. Because there's not too many possibilities to get an 8 or 10. So this is a different probability distribution. Okay, so I'm just going to keep going for a little bit. Those students who joined, I think you'll be able to follow this next bit. But any questions so far? So the graph of this distribution, by the way, looks a bit different than the other one. If I were to plot it, the probability distribution, basically I would plot the y, the values of y, and here I would plot the values of probability of getting that, and it would be a bar chart, and I would do 2, 3, 4, 5, and all the way up to 12, 6, 7, and I should have maybe given myself a little more space here. Let's see here. It turns out that this will be stepping up 1, 6, 2, 6, 3, 6, all the way up to the biggest one. So it looks like a bar chart, and it's dropping off. So that would be the probability distribution for adding 2 different dice. So I'm just going to mention briefly a little bit. Yeah, I'll mention this part. So maybe like another, let's say 10, 15 minutes or so. So those students who just joined us, we're talking about ways of describing something called a random variable, where we label the random variable with this big script letter, and we think of it as a chart where we have a lowercase letter, like a lowercase y, if the random variable is capital script y, and this little y could take on different values, and the difference between a random variable and a regular variable is that it's similar to just like, if you have a variable y, you can take on different values like this, but the difference is that with each value that it takes on, there's a probability associated with observing that value. That's the main difference. That's why that's where the random part comes in. Okay, so there's another type of random variable that we're going to talk about. These are types of random variables that are called discrete random variables, where the idea is I can actually list out all the possibilities that you might get, and I can tell you the associated probability of each outcome. So I think of the possibilities that the variable can take on as outcomes. There's another type of distribution or random variable, a very kind of interchangeable. There's something called a continuous probability distribution. Continuous probability. And this helps us answer the following type of question. So pick any number, and it's an interesting philosophical question. Pick any number from 0 to 10, and I'm going to say real number, not just an integer, but pick any real number from 0 to 10 equally likely. What is the probability that you guess 7? Or that a student would guess 7? What do you guys think? If I ask you, pick any number you can think of, right off the top of your head. It can have a decimal, square root, whatever you want. It's just got to be between 0 and 10. What is the chance that you pick a 7? Demetria, I like your answer. What did you suggest?
It seems like 0 because there's just an infinite number of things you could pick from. So there's no reason you would pick 7 over 7.01, 7.001, 7.001, 000, and so on.
Exactly, that's right. So when we talk about things that have a continuous spectrum of possibilities, and rather versus a discrete spectrum where you can, a discrete set where you can kind of list them out, you can't list out all the numbers from 0 to 10, all real numbers from 0 to 10, because like Demetria pointed out, like, how do you know what decimal to stop at? So this, if I ask it like this would actually be equal to 0. Since the event that we're talking about is a single event, but the denominator of the sample space is infinite. So how do we get around this? Because I do want to, like, it is a reasonable thing to say, hey, shoot a dart, like, and it can land anywhere on this, like, on this wall from 0 to 10. Like it's a 10-foot wall. Sorry, it's a wall that's 10 feet wide, and just like shoot a dart. What kind of, and the dart might just land somewhere randomly on this wall. Instead of asking, like, what's the chance that it lands exactly at 7 feet? What might be an alternative question to ask? If I want to understand, like, something about where that dart is going to land. Something else we can answer. This might be, you could imagine a real life situation where you're just talking about something happening completely randomly from any number from 0 to 10. What kind of things could we ask? We don't want to ask, like, specifically, can it land at like position 7? Because that would always be 0. There's something specific like that happening. The chance of that is technically going to be 0. But what is something that we could try to understand? Any ideas? basically, to get around this problem of like, well, you have an infinite number of outcomes, instead of talking about specific outcomes, so when we work with a continuum of values, or like basically values that can be in a set of real numbers, instead of talking about probabilities of specific values and specific outcomes, we talk about probabilities of an interval. And we can talk about the probability of landing in some range. For example, if I pick a number, if I ask a student to pick a real number from 0 to 10, what would be the probability that that number goes from 7, that random number x goes from 7 to 7.5? What do you guys think? What would be the chance of this?
Still 0.
This time
Wait.
not 0, because it's a range of numbers. I'm not saying it has to be exactly 7. It just has to be between 7 and 7.5. Dimitri, what did you suggest?
1 in 20.
Yeah,
Because this, you can sort of now that you have intervals, you can just count. You have 20 half a number intervals,
Mhm.
and then you're only taking one of those.
Yeah, you can think of it as, now rather than comparing, like, you know how we did when we first did probability, we talked about the size of the number of outcomes in an event divided by the sample space. Well, now we can no longer talk about like the number of things inside of an event. This event has like the number of numbers between 7 and 7.5 is infinite, but we can talk about the length of the interval. So we can actually measure how long the interval is. So that interval is a half of the unit, divided by 10, which is the length of the entire thing. So this just becomes 0.5 over 20 is like 1/2 over, sorry, 0.5 over 10 is just the same as 1 over 20. And I can just draw it for you here. 0, 10, then 7, and 7.5. And it's like asking, what's the chance, assuming that everywhere from 0 to 10 is equally likely, what is the chance that you land in that red region? Well, it's just going to be a half divided by the overall. And Dimitri made a good point here. In this case, because I'm just talking, we really only care about the infinite, like all the possible numbers from 7 to 7.5. If you modify this just a little bit by making, doing this, making greater than or equal to or less than or equal to, it's not going to change the results. Because including the 7 or not including the 7, in the grand scheme of things, doesn't really matter. So we use continuous distributions when we talk about having some sort of outcome that comes from the real number. And so this example that we did is something called a uniform distribution. Where all outcomes are equally likely. Okay, and I want to show you another idea here. So this is analogous to the picture that we drew earlier, but it's something called the probability density function. And we use the term density to kind of represent that it's no longer a bar graph, but it's going to be some sort of continuous graph that when its height represents kind of how likely you are to be in a certain region of the x-axis. But yes, the way we got 0.5 is just the difference here, just the length of this interval. This is 0.5, and the denominator is length. So I'm going to draw the probability density function for something that's uniformly distributed. And it's going to be really, really similar to what we did with the dice, but there's a subtle difference to it. So what I draw here, let me draw it. What I would draw is like this. So this would be all outcomes, and this would be the probability density function, P of x. Now I can no longer, you guys realize I can no longer do it like a chart like I did before with the dice. Like one was what, chance of getting a 1 is a 1/6, chance of getting a 2 is 1/6, and so forth. Because really now the chance of getting a 1 is 0. The chance of getting a 2 is 0. So I can't talk about it like that. But I can do something interesting. So what we do is we draw from 0 to 10. These are our possible outcomes. And then I draw a graph, a continuous graph over that interval. And in this case, it's going to be uniform. And what the graph does is it captures the idea that the probability of being in a certain region should be equal to the area under the graph. So the entire area under this graph is the entire probability. So entire probability. And it has to be equal to 1. So if the entire probability is 1, then the height here is 1/10. And the idea with the probability density function is that the actual value, the actual function value of it doesn't matter. We use, or it's not super, I won't say it doesn't matter, but it's not a super meaningful number. What's really important is that we use this sort of density function, or this graph, we can use it to calculate the probability of falling in a certain range of outcomes. So for example, what is the chance of going from, what is the probability of being from 7 to 7.5? Well, that's going to be, according to the probability density, it's just going to be the area of this little rectangle. So the area will be the distance 1/2. So the area of the red rectangle is equal to 1/2 base times height, 1/2. So it's just 1/2 base times height, which is 1/2 times 1/10, which is 120. So that's the idea, is that the area under the probability density function represents the probability. So I'll just kind of leave off here with this is a uniform density function because the density function is just a flat line. So that means that any interval that you pick, no matter where it is going to be the same probability, as long as it's the same base, the same like width. But of course, you can have lots of different continuous types of pictures. So I drew an example here. So there are many types of probability density function, but there are many types of and you'll see some in the homework. Density functions. And the only restriction is that they're always positive. The graph, they're always greater than 0. And the area, the total area underneath the graph is equal to 1. That's what makes it a probability density. So let me just show you an example of the probability density, and we can interpret what it means. So I'm going to draw a picture like this, and this will be, no, I'll let you guys go. We'll do some more examples later. So this is x. This is going to be the probability density axis, P of x. And I'm going to draw a triangle from 0 to 6 and height 1/3. First, can you guys confirm? Yes, P of x has to be continuous, and it also should be continuous. Can you guys confirm that the area of this triangle, so the function P of x is the one that I'm highlighting in green, it's 0 everywhere, but then it makes the triangle shape, but then outside of that, it's still going to be flat. So can you guys confirm that the area inside the triangle is equal to 1?
Yeah.
Right. It's just base times height. You know, base 1/2 base times height. 1/2 base times height is 1/2 times 1/3 times 6 is equal to 1. So this is area 1. And we can use this picture, and this is kind of a weird one. Based on this, our outcomes are ranging from 0 to 6. What do you guys think? If you were like throwing a dart, and according to this probability distribution, would you say that you'd be more likely to, based on this probability distribution, would somebody be more likely to pick a random number close to like between 0 and 1, or between 5 and 6? Which one would be more likely? Nice. Lily, why do you say 0 to 1?
Because the area there is bigger.
Exactly. That's it. So this is a way, it's kind of like when we have a histogram, we might have bars that are not equal height. This is just the continuous version of that. All right, guys. And so to find the particular area from 0 to 1, just mentioning here, you could use, like when it's triangles, you can actually just use geometry, and you could try to figure out by using the trapezoid, like try to find the area of the purple region. So, all right, here probability that x is between 0 and 1 is equal to the area of the purple trapezoid. And there's clever ways to do it. You can actually do the 1 minus this triangle. This triangle is actually pretty easy to find. Yeah, we're not going to do too much with that, but that's just kind of some of the ideas. We're going to actually do more stuff where the probability distribution will be a curve, and you actually need to use a calculator to find the area underneath it. But that's just that should give you enough information to start working on some of the homework. And next time we'll talk about this in unit. All right, guys. Those of you who are in the first section, remember test on Tuesday, and I will see you guys then. All right?
Thank you.
Have a nice weekend. See you.
Thank you.
Wait, what's the formula for an area of a trapezoid again? I forgot.
Yeah. Okay, good question. So this one I would probably not do it that way because I would do the big triangle minus the small triangle. But for a formula of a triangle, or area of a trapezoid, let me do it, like this. Actually, let me draw. I'm going to draw it on its side, okay? There's a nice way to see it. Do you see if we take another trapezoid and we stick it on, what shape we get? If we do a 180 reflection or something? What's the area of the big shape?
that? Can you say that again? Sorry.
If we take this trapezoid and we do a reflection of it, and then we rotate it and stick it onto itself. Do you see that it forms a rectangle? And the area of the rectangle would be h times b1 plus b2. So, but we want the trapezoid. So the area of the trapezoid is going to be 1/2 of b1 plus b2 times the height.
Okay, thank you. Have a good day.
Okay, you too.
Has class been permanently moved to 2?
Yeah, I haven't. So I think I'm going to do that just to. I'm going to extend this class, like keep the first class and just go like from 2 to like 3:30 or 3:20.
2 to 3:30. All right.
But yeah, I know. Do you guys have any questions? I went over like some of the stuff from the practice, and also kind of you guys didn't get to see like the idea with the discrete distribution. So I could just go over that really quick if you want to see that. But do you guys have, before we do that, do you have any questions from the practices?
Oh wait, class starts at 2. I thought it started at 3. I was kind of confused why we ended early, but we didn't.
Oh no. Yeah.
We're gonna have to watch this back.
Yeah. So sorry. I just like so the previous class I started it at 2. It started normal, but I went over the practice test before, so it kind of pushed the entire class a little bit pushed it into this next one. But I think I'm just gonna keep the class. I'm gonna move the 3 o'clock class. I'm just gonna do everything at 2 o'clock. And so this one, I'll have more time to go over. I'll do from 2 to 3:30. Because I think the upcoming classes, I'd like to have a little more time to go into the concepts.
Okay.
And if you have trouble making them, I'll post the videos. And I'll also be like, you can always, I'm happy to discuss, especially if you know, I know it's sometimes hard to learn from videos. So I'm happy to meet like something during the weekend, an office hour, or after class as well.
Yeah, I'll probably come in for office hours, I guess.
Okay, yeah. Or you can jump in like some of the classes I'll post the videos ahead of time because I have some of them pre-recorded, so you can jump in like towards the end as well.
Okay, bye.
Okay, yeah, and then I'm happy to. Do you guys have any questions from the practice?
No, I don't.
Okay, nice. And then yeah, just to say the thing with the discrete probability is pretty straightforward. Like there's 2 types of random variables. Just there's discrete random variables and continuous random variables. The idea is that you guys jumped in when it was continuous random variables. Like the outcome could be any sort of number from a continuous from an interval on the real number line. A discrete random variable is where the outcome has to be like from a finite or something that a set of values that you can actually list out. So like rolling a dice is a good example of a discrete random variable. And one way to think of a discrete random variable that's really nice is as a chart where you have the set of possible outcomes and then you have the set of associated probabilities. And the last thing, does that make sense?
Yeah, it does.
And the only tricky thing, and it took me a while, like when I first learned about random variables, like it didn't quite click why they're interesting and what they're useful for. It's just another way of representing like a random event. And so we use capital X, capital script X, to represent the entire chart or the entire graph. Like that's what this whole thing represents. Little x is like a variable that can, a placeholder that can take different values with corresponding probabilities p of x. And the interesting thing is that how you work with these. So if you have script x times 2 or script x plus script x, that would be the random variable that corresponds to just just doubling whatever you get on each die. So that would be this chart here. Or another way of looking at it is like as if a scientist rolls a dice and records that number and then writes the same number again, writes that same number 2 times. That would be represented like this. And that's different from letting x1 be a die and x2 as another die, and looking at x1 plus x2, where they are x1 and x2 are independent dies. That's the case where we discussed, like when we first talked about sample space, where you can roll a die and roll a second die and talk about their sum. And we saw that the chance of like rolling a 2, like getting a 1, this only happens when you get a 1 and a 1. That's a 1 out of 36 chance of happening. And the most likely outcome is actually you'll get a 7. There's 6 ways that could happen out of 36. And then it goes down to 2. So you get this interesting sort of, if you look at what we call the distribution, which is the graph of these outcomes and probabilities, you get this sort of little triangle graph. So that's the only detail I talked about in this week. Yeah. Did you have any questions?
No, I didn't. Thanks.
Right. Yeah, I posted the homework and the test will be on Tuesday.
Cool. Thank you.
Okay.
Bye.
See you.